Hello, my name is Bob D. Hilster, and I am your particle model guru. I'm here today to talk about the magnetic field and what is it. As defined by Wikipedia, and I'm assuming that's mainstream's idea of what a magnetic field is, I'll read, a magnetic field is a force field that is created by moving electric charges, which they're saying is electric current, and magnetic dipoles, and exerts a force on nearby moving charges and magnetic dipoles. And at any given point, it has direction and magnitude, which means strength, so it is represented by a vector field. Well, there's some questions you might have about all this. I could ask questions when they say an electric charge, are they talking about an electron or a proton? Question is, what's causing it to move the way it does? Where do they come from? Where do they, if the charge is negative, do they repel each other? These are just some of the questions you would ask of the people writing this so you could understand it better. The Wikipedia article then goes into a brief history, and then they get into equations, the B field, the H field, and so on and so on, but not too much in terms of an answer. But here is a drawing of a battery and a wire and a magnetic field around the wire, taken from the link shown. And this particular diagram shows the right-hand rule because out of the battery, we have positive current flowing this way, or out of the positive side of the battery through the wire, back into the negative side, so the current flow is this way. And if you use your right-hand rule and put it there and point it in the direction that the red arrows are, you'll see that in fact the top of the magnetic field is coming towards you and the bottom of the magnetic field is moving away from you. Electric current, right-hand rule. That's N. They're clearly in circles. The path is circular. So why is it circular? Well, this is one way you can determine which direction the magnetic field is going. So you take the wire and you make it vertical, and you push it through a surface, and on the surface you place compasses, and in each compass is a little tiny magnet. Now here they don't show you which direction the current is going in, and they don't really show you which direction these are going. But you can imagine that with the right-hand rule and electric current going up, that the magnetic field would be going counterclockwise around that wire. So you can see, it's pretty clear. Well, obviously those are moving in circles. That's what it looks like. When you draw a line through each magnet into the next magnet, you get circles. And I throw out the question, we'll come to it in a minute, is there more to that flow than just circles? Well, I did a video really early on about the title was The Right-Hand Rule Becomes a Left-Hand Rule. That's the link, you can go view it. This was a video I did off the cuff. Dave asked me a question and I just started talking. But I claim that the left-hand rule is deterministic and is caused by the flow of G1 particles and the structure of the copper wire. What I mean by deterministic is it doesn't matter what day it is. It doesn't matter what time, what hour of the day. It doesn't matter what year. It doesn't matter whether you're on the North Pole or where you are. The left-hand rule for a particle flow is always true. It's deterministic. Something has to cause that. If it's always true, 100% of the time, something is causing that. And that's what I tried to explain in the video, and I'm going to go into more detail here. Now, I have stated in other videos that the G2 gravity field is a nuclear binding force, the atomic binding force, and the molecular binding force. So the G2 gravity field holds the copper wire together just like G1 gravity field holds our galaxy together. So we have a G2 force around and through the copper wire holding it together. Now here's kind of a scary side point. I'm just throwing this in. Without the G2 particle and the structure field that it builds up around objects, not one object will hold together. All objects, including us, including me, including you, will fall into millions of tiny little particles. Wow, that is scary. But even if you do not agree with the idea, think about what happens when mainstream determines what the nuclear binding force really is. And without that force, we simply disintegrate. So, not really saying something new, but I'm saying it, whereas other people aren't saying it. You've got to have the nuclear binding force, the atomic binding force, and the molecular binding force for us to be held together. It's scary thinking about the possibility that it would not be there. Okay, so we go to the copper wire and the atom, and I'm showing this particular one because of two reasons. One, it starts to show you an organized structure of copper, where the atoms are nestled towards, it's not detailed, very detailed, but then it shows you a picture of an atom. Now, this is the classical model where the nucleus is made out of protons and neutrons, and there are electrons orbiting. In the particle model, we've changed that. There are no protons and neutrons. There is only nucleons, and the electron is replaced by the G1 particle as a G1 orbital. But look at the open space. There's a lot of open space, not only inside the atom itself, but in between atoms. There is probably also other space. And just as a side point, which this will come up later when I discuss circuits, an object is a better conductor when there is lots of open space. An object is a poor conductor when there is less open space. And so with this open space, the G1 particles, which are acting as electrons, but they're G1 particles, they move easily through copper because there is lots of open space. Lots of them just plain go straight through the copper wire. Okay, so let's look at the more organized structure of the copper. And I'm going to look at the G1 flow in this copper as if for example, the G1 particles coming from the left, like by the arrow I'm showing, and it comes here. Well, inside here is this G2 force field holding these atoms together, and that's G2 gravity, okay? G2 gravity. G2 gravity is holding G1 orbitals in orbit around each atom. So as a G1 particle comes through, it would be attracted towards this one, and then this one, and then this one, and this one, going up and down. As it goes through, it might go down and then up and then down and then up. Either way, in a vertical sense, it is snaking through vertically, down and up, down and up, down. If you flip this or put yourself on the top, looking down, and so now this is the top surface. I have the same thing. I have a G1 particle coming through, and it's going to move left, then right, then left, then right, then left, then right. So it snakes through horizontally, goes horizontally through like this, or it goes vertically through like that, which to me makes a path look like a spiral. Maybe not a perfect spiral. Certainly they're all coming in at little different places, but with a lot of open space, most of them go through. Some of them hit and scatter off in all directions. Some of them get trapped. If they come in just right, they can get trapped and stay there as an orbital. So there's a spiral-like pattern to the flow of the G1 particle in the copper. So now I'm going to look at the end of the copper wire, and I have shown here a bunch of particles flowing into the paper. It's flowing in because I have an X here looking like the rear end of an arrow. And so all of these are moving into the paper, into the wire, and they're going to be all over the place, all over in the middle, throughout the whole center, and at the edge, flowing through the copper wire. So when some of them escape, now they may escape naturally because they were at the edge and they just sneak out, or they could bounce, they could scatter out, hit and scatter. I'm not sure, but somehow they get out. And if these, again, I got these are showing the particles after having left the wire. If they're scattering and they move straight out, they could be lost. But some of them could actually get trapped by the G2 force field that's around the wire, holding the copper wire together, holding the atoms together, and now keeping some of these there. So what you have now is you have motion. You have these particles moving into the paper. And if they're moving into the paper and you're using your left-hand rule, you point towards the copper wire and you'll see that it's going to be going counterclockwise. So I've drawn the arrow. Now, I really don't know the exact mechanism for this to happen, except that I know that the copper is organized. I know from tests that the field is going to be counterclockwise using a particle model and the left-hand rule. It's going to be counterclockwise. A lot of work needs to be done to study this geometry and the possibility of how this works. I can't claim to have a complete, precise answer here. What I am claiming is that it is the speed of the G1 through the wire. It's the organization of the copper in the wire, excuse me, and it's the G2 force field around that, I'm sorry, that keeps them there. And they're going to look like they're moving in a circle. Why? Because if I go back to a different picture, the pitch of which I didn't cover, the pitch as the G1 particle comes in, it goes up, down, and up. So the pitch could be as tight as the atomic spacing, which is probably in the order of 200 picometers. So the pitch of this snaking effect could be that low, but not necessarily, because with the G1 particle moving at speed c going so fast, it might actually have a much slower pitch, a longer pitch than that. But regardless, it happens. To me, it's the speed of and direction of the G1 particle through there. It's the organization of the copper. It's the fact that when you have a lot of G1 particles flowing through a circuit, you get a strong G2 force field. Remember in the double slit experiment with the detector, when the detector had current flowing through there, a strong G2 force field develops and interferes with the interference pattern, destroys the interference pattern. So all I can say is it's a very good starting point, and it has a possibility. Otherwise we don't have an explanation. So what is the magnetic field? The magnetic field around a wire, a coil, or a magnet is a stream of high-intensity G1 particles with no apparent pattern. By comparison, Newtonian gravity is a stream of low-intensity G1 particles with no pattern, and the magnetic field is the same thing with a high-intensity field of G1 particles. So we get back to the circuit like I showed before with the battery. In this case, I have the G1 particle flow coming out the negative side of the battery through a current limiting resistor. Got to have that, or this will blow the wire. The battery will blow, the wire will get hot and blow. So you have a resistor, and then you got the flow of G1 particles this way. You got the G2 force field around the wire, and I'm expecting that based on this, where if you use the left-hand rule again, the particles are going this way, and the magnetic flow was going to be at the top. It's going to go into the page, and from the bottom, it's going to come out of the page. So you have you got the copper wire being organized, you got G1 flow through there, you got a G2 field around it, maintaining this, and this is drawn with a very wide pitch, which is only done that way for clarity. So we were asking questions earlier about what Wikipedia said. Is that an electron or a proton that they call an electric charge? And what causes it to move? Where do they come from? Do they repel each other? So on. Particle model answers are this. It is the G1 particle, and it has no charge. Remember, the particle model, there is no positive and negative charge. Where do they come from? They come from the battery, not the wire. They could also get trapped from the G1 field around the outside, but if they came from the wire, eventually the wire would disintegrate. The wire doesn't disintegrate, so they can't come from the wire. What causes it to move? What causes the G1 to move? It was already moving at speed c as a G1 orbital in the battery, and released through a chemical process. There is no EMS force pushing the G1 particle. Again, there is no charge, plus or minus charge, and there is no EMF force. The G1 particle is already moving at speed c. Do they repel each other? No, they don't repel each other in that sense, but they do bounce off each other like billiard balls. So in conclusion, we can compare three different things. Newtonian gravity is a stream of low-intensity G1 particles with no pattern. I didn't spell pattern right here. The magnetic field is a stream of high-intensity G1 particles with no pattern. Light is a stream of G1 particles with a repetitive pattern and can be high intensity or low intensity. All of these streams move at or about the speed of c, but are different in how they are organized. My name is Bobby Hilster, and I am your particle model guru. Tune in next time when I'll explain more of the universe using the particle model. Thank you for your attention.